Welcome to this ongoing lecture series in group theory. Today we'll be proving the fundamental theorem of arithmetic. And let me not recall anything from the last time because there is not much to recall. It's basically Euclid's theorem and a few facts about GCDs that we collected over the previous lectures, and I think I'll anyway go over this one in good amount of detail, so we don't need to recall anything. So these are the problems, and now let us just quickly start. Right, so first of all, we have a very simple fact that every integer can be written, or let me just say natural number, because everything can be stated for integers, but let me, for simplicity and for avoiding some trivial errors, stick to natural numbers. So every natural number can be written as a product of primes. Now this is also wrong, so I should say n greater than equal to 2. Why was that wrong? Because if I take n equals 1, I cannot write 1 as a product of primes because 1 is not a prime. So there. So deliberately I started that way. Right. So n greater than equal to 2, any such natural number can be written as a product of primes, and this is very easy because if n is not a prime, then it is composite, meaning it can be written as product of two things which are both not equal to 1. Right? It has a divisor which is different from 1 or itself, and therefore the other guy that you'll see will also be different from 1 or n. So you can write n in this fashion. And now since a and b have strictly smaller size than n, you can appeal to inductive reasoning and say that, well, a can be written as a product of primes and b can be written as a product of primes, and therefore n can be written as a product of primes. So the proof here is just induction or well-ordering principle or whatever you want to call it. Well-ordering principle. And I encourage you to write down the full details if you do not have practice with such things. Alright, so every natural number greater than or equal to 2 can be written as a product of primes. Great. Now this is a direct corollary. So suppose again you have a natural number exceeding 1. Then there exist pairwise distinct primes p1 up to pk such that n is of this form, p1 to the e1 dot pk to the ek, where each ei is a natural number. It looks complicated, but it is nothing. So what you do is you write n as a product of primes, whatever p1, let me say n equals q1, q2 dot qr, and then whichever primes repeat, you collect them in this fashion. So you just get an exponent. So if p1 is a prime appearing in this q1 up to qr, so the number of times p1 repeats is this e1. So that's it, and that's how you will get such a thing. So this is immediate from the previous lemma. Alright, so we have that, and now before we get to the statement of the fundamental theorem of arithmetic, we have this very simple, or okay, not very simple, but a fact that we have seen in various avatars before. So here is it. So suppose you have two relatively prime integers, which means that their GCD is 1. Then for any natural number n, we have that these two things are also relatively prime. So let me give a proof for n equals 2, and then I will leave for you to prove it for higher values of n. It's the same idea. So since GCD of a comma b is 1 by hypothesis, by Euclid's theorem there exist x and y such that ax plus by is 1. And now I will square both the sides. So if I square both the sides, I will get a square x square plus b square y square plus let me write it in a different fashion. So let me write 2abxy plus b square y square equals 1. So that, and now this implies that a times some integer, which I don't really care what that looks like, but let me write it. A times that integer plus b square times some other integer is 1. So if D is a common divisor, so if D divides A and D divides B square, then D divides the LHS, which implies that D divides the RHS, which implies that D equals 1. Well, I'm taking a positive common divisor, so D is at least 1. So this shows that the GCD of A and B square is 1, and you can, for higher powers, you can just appeal to binomial theorem, which you must have learnt in high school, and instead of raising to the power 2, you can raise it to the power n, and the same argument will go through. Alright, so very simple thing. And although we did not really need that, but anyway, it's good to keep that in mind in order to follow the proof of this guy. So what is this guy? This is the fundamental theorem of arithmetic. And it says that again, you have some natural number exceeding 1. And suppose you have found primes, and let's say they are in increasing order, such that n can be written in sort of two ways. So first, this is first representation of n as, powers of distinct, product of powers of distinct primes, and this is another representation of n as product of powers of distinct primes. The fundamental theorem of arithmetic says that no, these are not really two different representations. So it says that actually the number of pi is the same as the number of qj's, so that is encoded here, and the primes are the same in order. Further, their exponents are also the same. So there is essentially a unique representation of a given integer of this sort as a product of prime powers, where you just assume that the primes are arranged in an increasing order. So you can change the order of these primes, but that's essentially the same representation, and that is why I have imposed this condition. So if you impose this condition, then there is no question of reordering. So anyway, I hope you understand what I'm trying to say. So we need to prove it. And first, I will prove that. So first we'll show that K equals L. So assume on the contrary, so rather than that, let me say if K is not equal to L, then we may assume without loss of generality that L is exceeding K. Because you could say, well, of course, K could also exceed L, but that's exactly the very symmetric situation. So arguing here is enough to argue the opposite case. So that I will leave. I will just argue with this case. So suppose L is greater than K, and then we'll arrive at a contradiction basically. Okay, so suppose L is greater than K, then, so here is a key step, then there is some J such that, so some J in this range 1 up to L such that Qj is not in this list of primes. So the way I've written it may look a bit complicated, but here is what I'm trying to say. I'm saying if L is greater than K, then you are seeing more primes here than you are seeing here. So there must be some Qj amongst all these Qis, or there must be some particular Qj which does not appear in this list of primes P1 up to Pk. So that's what I've written here. All right. So then Qj divides this Q1 to the power F1 ... Ql to the power Fl. Why? Because Qj is of course, Qj appears here, so Qj divides that, of course. So this implies that Qj divides n, because this is equal to n, which implies qj divides p1 to the e1 dot 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 p what was that, k, yeah, pk to the ek, right? But qj is not appearing anywhere here. So qj is relatively prime to p1, qj is relatively prime to p2 dot 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 qj is relatively prime to pk. So since qj is relatively prime to pk, I mean, I'm just arguing for pk. So since qj and pj have GCD1, qj and pk have GCD1, we have by the previous lemma that the GCD of qj and pk to the ek is also 1. And now these kinds of things we have seen in the previous lecture, that qj divides product of two things, and the GCD of qj with this guy is 1, so it should divide the remaining thing. So therefore qj must divide p1 to the e1 dot 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 pk minus 1 to the power ek minus 1. We saw this in the previous lectures. I also gave this kind of thing as a problem, so I hope you are convinced. And you keep repeating this argument. So ultimately, if you just keep doing this, you will end up with the fact that qj divides p1 to the e1, which is absurd because qj and p1 are relatively prime, and hence qj and this thing are relatively prime, which really implies that qj equals 1. Which is a contradiction because qj is a prime. It cannot be equal to 1. 1 is not a prime. So that's it. So if you assume that L exceeds K, then you get a contradiction. If you assume K exceeds L, you again get a contradiction. So this is not possible. Therefore, K must be equal to L. So we have shown that. K equals L. Alright, so now what we need to show is that all these primes are the same, meaning P1 equals Q1 and so on. So here is, again, it's exactly the same argument that we just gave. So the argument that we just gave actually shows that Qj must appear in this list. So what we just showed, what we have shown is that this contains Qj for each j. J equals to 1 to L, but we have established that L equals K, so I will write J equals 1 to K. Why? Because if suppose there again, so it's the same argument. If there was some j such that qj does not appear anywhere in this pi's, then this division will again imply that qj equals 1, and that would be a contradiction. So what this means is that this chi, I'm just doing it in gory detail. So this chi contains that chi, and you can show the reverse containment. So this implies that, in fact, because the two sets have the same size, you can just say that the first set is equal to the second set. So since P1, P2, P3, they are in increasing order, and Q1, Q2, Q3, they are in an increasing order, then this also implies that P1 equals Q1 dot 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 Pk equals Qk. So we have shown so far that this much. We have shown this, we have shown that, and now the last part, it is also very, very similar. So what we can do is that we can write that n equals p1 to the e1 dot 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 pk to the ek equals q1 to the f1 dot 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 qk to the fk, because we have shown k equals L. So now again, suppose fk exceeds strictly ek, and we'll get a contradiction. So then n by pk to the ek, which is an integer, equals p1 to the e1 dot 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 pk minus 1 to the power ek minus 1 equals q1 f1 dot 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 qk minus 1 fk minus 1 qk fk minus ek. Now this prime qk does not appear anywhere here, but this has a positive exponent. Since fk is greater than ek, this exponent is positive, and hence this guy, or I should just say the qk, therefore divides the right hand side, and hence it also divides the left hand side. But in the left hand side, qk simply does not appear, and the kind of argument that we just did implies that qk must be 1, which is a contradiction. So I'm not writing all of that. So this implies this is a contradiction, and hence what we must have is that fk is less than or equal to ek. But the same kind of argument will also show that ek is less than or equal to fk, and hence ek equals fk. And if we can do it for k, we can do it for any j, and hence ei equals fi for each I, and that's it. So let me not write down those things. You can do that yourself. So that's the fundamental theorem of arithmetic. It's a beautiful theorem, but having done all the previous work, it is kind of trivial. Alright, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.